Hello and welcome to this new video where we discuss mathematics and physics on the board. Today what we are going to do is basically use a result that we derived in a previous video, in a more mathematics video, and here we are going to use it to introduce what are called Lorentz transformations. Now they are mostly essentially mathematical, but they are obviously applied in physics in the context of special relativity. So that's what we are going to see today. Right, so just a little bit of summary with what we've seen in a previous video that should appear somewhere kind of here. And the idea is if you have a space here, the result we had obtained was simplified to R cross R. And essentially this is in general R cross R to the power n, and here we've just chosen n that is equal to 1. But the reason why it's written that way is because the zeroth coordinate has a different role as opposed to the other n coordinates that may appear in this space. And so here we have defined a Minkowskian inner product, and for any two vectors uv in that space, and this is basically defined as u naught v naught minus u1 v1, and that's in kind of in orthonormal kind of basis. Okay, that this is going to look like that. Now, what we had found is that we had looked for an isometry L. And isometry means that if you look at the inner product of LU with LV, then you're going to get the same as the inner product of U and V. Okay, so here we had looked at a special isometry which has the determinant +1. And what we had found is that if you have some alpha that belongs to the reals, then L, this matrix, is going to have this particular form and involve basically the hyperbolic trigonometric function. So cos alpha, sine alpha, cos alpha here. Now, to be honest, that doesn't talk to us very much. I had actually put an animation. Maybe I'm going to put it here and display what this transformation is going to look like here. So just for a few seconds so that you can see what it looks like mathematically. Traditionally, if you have here a plus sign, that would be a rotation like this with a certain angle. And if you have a minus sign here, you get actually some sort of hyperbolic kind of transformation of the vectors. Okay, so now that this is kind of summarized and reminded, now we can move on to trying to get to these Lorentz transformations, at least in the form that they are seen in physics, okay, or theoretical physics. So the basic idea is to actually put or define the quantity beta, and you say that beta is equal to tan h of alpha. So I think a first thing we need to do here is to basically see, like mathematically, what does that entail. So if you plot alpha and on the x-axis and beta as tan h of alpha, then what you're going to have is, that's not at the right place. What you're going to have is, let's put here -1, is essentially a function like this. Okay, it's not perfectly done. Usually it should be a straight line here around 0, but this is going to be a variable beta that is bound from below by -1 and bound from above by +1. And we are going to see that this is actually very meaningful indeed. So here at that stage, what we need to do is remind ourselves of some properties of this hyperbolic tangent. So for example, we have that 1 minus tan h square alpha is equal to cos squared 1 over cos squared alpha. Okay, And so what that means here is that 1 minus beta squared is equal to 1 over cosh squared alpha, and consequently this leads to cosh alpha is equal to 1 divided by 1 minus beta squared. And then finally, so that's kind of one thing is this, another thing is that, and then we also have that cosh squared alpha minus sin h squared alpha is equal to 1. Okay, so that's another property. So here, that's, again, this is kind of the important equations we're going to use. And this is an identity. This is another identity of the hyperbolic trigonometric functions. And so what we get out of this is that we can get that sin h squared alpha is equal to cos squared alpha minus 1. And so that's equal to 1 divided by 1 minus beta squared minus 1 minus beta squared, 1 minus beta squared. And so if I now apply it there, I'm getting basically that sine squared alpha is equal to beta squared over 1 minus beta squared, and that's equal to beta, and then 1 divided by 1 beta squared square root. At that stage, what people do is essentially define cosh alpha. They actually decide to denote this gamma, and this gamma is traditionally called the Lorentz factor. And then to the extent that what we are going to get in the end is the following. We are going to get that the matrix L is going to be gamma, then beta gamma, and then gamma here. Okay? So that's kind of the idea. And then what we are going to do here is basically move on. So at that stage, this gamma again is called Lorentz factor, etc. And to go into Lorentz transformations, what we need to do is essentially now move, let's say, from the relatively abstract description we had done here, and now we are going to move into R cross R3, okay, where in this particular case, this particular variable here is associated to time, and then the other one here is associated to, or the other ones are related to space. Okay. Now, because you want them to have the same kind of coordinates, you may want to use x naught if you want. So for the time being, we are going to use here. I'm going to keep the same as this. I don't need necessarily for now to use any different kind of things. So here that's going to be x1, x2, and x3. You can think of them as being x, y, and z. And then what you say is that you're going to, if you imagine, let's say, two vectors, so that I'm going to put like this with a bar below, so x, y in R cross R3. Okay, so let's assume these are some vectors. Then you define the inner product as being between x and y, as being essentially, so this is x naught, y naught. So again, this 0 corresponds to some sort of time coordinates. By the way, these things here do not represent positions of things. Well, they do in a sense, but essentially this object here, characterized by giving these things, is going to correspond to the notion of an event. So in that case here, any of this collection of coordinates gives you an event. And so here you've got basically two events, and you look at the inner product between these two events. And this is going to be minus, and then that's There are multiple ways to write it, so that's x1, y1 minus x2, y2 minus, no, that's not x, yeah, minus x3, y3. Okay, sometimes people would just write it as x naught, y naught, and then minus x, and then dot y, where it's understood that the x and y with a vector on top is going to correspond only to the spatial part of it. Okay, so in that case, we can look at the corresponding vector here. A transformation here that is going to make this thing invariant, and this is going to be L. And then in that case, what you can do is put yourself in a correct, let's say, basis or coordinate system, such that it's going to have this particular object. So you define your x-axis such that the transformation is going to act only on the x-axis and the x-naught axis. And then the x2 and x3, for example, are untouched. And so usually in that case, the transformation looks like this: gamma, then beta gamma, and then you put here 0, 0, and then you put beta gamma, gamma, 0, 0, and then you put here 0, 0, 1, and then 0, and then 1, 0, 0, 0. Okay? And so this particular transformation is actually what is called the Lorentz transformation. So that's, I mean, sometimes people would say that this is a Lorentz transformation, and that's not entirely kind of false, but it's basically a subpart of it. It needs in principle to apply to the entirety of R cross R3. So this would be then the Lorentz transformation. And what this does, again, is basically to make the inner product essentially invariant. So not in particular, it's going to make invariant so x with any y, but that includes as well x with itself. And that's something we are going to look at in a different video. So that's the Lorentz transformation. The last part to actually get into physics that I'm going to introduce is that we are going to say that essentially, for example, there need to be an additional interpretation here of that particular transformation. The first one is that the x naught component, so the naught component of any of these vectors, is interpreted as being c, some constant speed that now we interpret as the speed of light in vacuum. So interpretation, x naught is going to be equal to c times t naught. And so that's more traditionally how this is represented, and t naught would be the time interval we measure between an origin event and then the event we're looking at. C here is basically a sort of constant characteristic. Velocity, or speed, in fact, I should have said speed. And then what we do, so that's the first aspect, and once we have introduced that, then we introduce beta as being interpretable as a velocity here. So I'm going to say here, yeah, so I'm going to call that u. That's not a good idea to call that u, because u here was a vector. So let's call that differently. Well, v as well was a vector, to be honest. But maybe I can call that v of whatever, r prime, and then divided by c. And so maybe I will do r prime relative to r. And where here, basically the way we interpret what's going on is basically by saying that actually the transformations we're looking at corresponds to a transformation of coordinates that is akin to what happens when you switch between frames that move at relative velocities v r prime r in along the x1 direction. Okay, so along this x1 direction, essentially you've got a particular motion going on at that particular velocity relative to the original coordinate system. And then when you want to transform into a new one that moves at that particular velocity, then you apply that transformation. Okay, so that's the interpretation that is given to that. But the bottom line here is that essentially the Lorentz transformation stems from an isometry or a special class of isometries of the Minkowskian inner product. And the reason why I want to insist here is because it really works for any inner product. So the inner product you take between any two kind of four vectors. And the reason why this is going to be important is because we are going to see that we don't necessarily take always like some ds squared that is inner product of dx with itself. We can do some other stuff. Okay, so that's kind of the bottom line. Here, of course, you need to kind of trust the interpretation I'm providing, which is that x naught is converted into c times t naught, where again c is traditionally interpreted as the speed of light in vacuum, and then beta is basically interpreted as this some velocity between then different frames. Now, the reason why it works like that, and that's one way to work it out, is basically to see how this thing is going to impact x0, x1, x2, etc., and see how that goes when beta basically tends to 0, or at least when it's much smaller than 1. And when you do that, you actually retrieve the Galilean transformation upon changing frame, and that's why basically this is interpretable as a sort of extended version of that. Okay. So that's it. Again, that was a relatively quick video. If you thought that there was some parts that were unclear, or you've got some comments or anything like that to put forward, by all means, do let me know in the comments, and I will be, it will be a pleasure to try to clarify some of these points, or even to go through the derivation I mentioned here, where we try to look at finding the limit when beta is much smaller than 1, and then from this we infer that actually it's a transformation upon changing frame of reference. Right, okay, so otherwise, see you in the next video.